Okay, example 3 is asking us to use a part of the disk method, and it's a different version. It's called the washer method. We'll see why it's called that in a second. But it's asking us to find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. So the first thing is you need an accurate picture of what this graph looks like. So the square root of x, it's going to look like this. And we have our x squared is going to kind of look like this. Okay, so this is the area that we are interested in, right here. Okay, now what's happening is we are rotating this image, which looks like this. So I'm going to kind of zoom in a little bit. We're rotating this image about the x-axis. Okay, so in a sense, like if we were to have rotated just y equals the square root of x, we would see that we would have a radius like this, and it would create kind of a big circle. Well, we're not rotating this whole image. We're actually just doing the area bounded between these two things. So we're like taking out this circle from the much larger one that we would have had before. So what we're going to end up with is kind of a washer type design. We're going to end up with kind of an empty hole where this would have been. And so as you can see, this area here is kind of this washer looking object, and it's going to extend all the way down. So the way that we deal with this is we take the volume that we would have found with our main graph, or our top graph, which we'll call, and we subtract away our bottom graph from it. We subtract away the disk from this. So it's just the difference in these two. That's how this is going to be set up. So we need to know, okay, so this is the square root of x, and this is x squared. And so, let me write this down here. And so this area here is the part that's being rotated around. So we're going to take our top function, or the distance that our top, more specifically, the distance that our top function is from our axis of rotation, which we've done before. So, and we're going to call this big R, the one that is furthest away. The graph that is furthest away from our axis of rotation. So this graph we're going to call capital R, and this is the square root of x. And we're going to call little r the smaller disk that we're taking away, the one that's closer to the axis of rotation, and that is going to be little r. Well, our disk method says that we are going to do the volume is going to be pi times the integral from a to b of our big R squared minus our little r squared. So what's really happening here, we can think of this as two separate integrals. We have pi times our big one, so we're basically doing this is a disk, and this is also a disk. We're just taking that one away. So this is the format that we need to plug this into. So I'm going to go ahead and try to find this. Well, we need to know what our bounds are. So what are the bounds for this particular graph? So if we would do the square root of x equaling x squared, this is going to occur. Let's say if we were to solve this out, we could square both sides. We get x to be the same thing as x to the fourth. We'd have x to the fourth minus x equals 0. We'd have x times x cubed minus 1 equals 0. So you'd be able to find pretty simply that the only possible solutions for this are going to be x to be 0 and 1. You can use a calculator to confirm this, but you should be able to solve for this algebraically. Okay, so now we need to input this information in. So we're going from 0 to 1. Our big R is the square root of x. And our little r here, is x squared. And so this is the formula that's going to give us the volume of this region. Okay? It's basically, again, it's the large disk minus the small one. And so I can tell this all by the picture. And so now I need to go ahead and simplify. So this is the same thing as the integral from 1 to 0. The square root of x squared is just x, and then x squared is x to the 4th. And so now I can go ahead and perform this integration. So this is going to be pi times 1/2 x squared minus 1/5 x to the 5th. And I'm doing this from 1 to 0. So we're going to get here pi times, if I plug in 1, I'm going to get 1/2 times 1 squared makes a half. I'm going to have 1/5 times x to the 5th, which is just 1 to the 5th, so this is going to be minus a 5th. And then I subtract away, plugging in 0, which this you can find very quickly is just going to make 0. And so I need to do 1/2 minus 1/5. That's going to give us 3/10 for this. So we're going to get, as an answer, 3/10 of pi for this area. The big key, again, we need a picture. We need to understand the area that we're finding. So we need the function, like our top function and bottom function, just like the difference of two curves. We need to know where we're rotating it around. So that's our radius. Our radius has to do not necessarily with just the function, but how far is it away from the line that we're rotating around. And then the disk method is going to tell us that the washer method is going to tell us that we basically are doing the difference of the outer disk and the inner disk. So we're making a washer. So, and that's why we have 1 squared minus the other squared. And so it's just very important to find the order. It's very important to find where our bounds are, and then to just set it up. And then we can let our technology do the rest. But you should be able to find that the answer is going to be 3/10 pi.